here is an orbital problem. It's really an energy problem, but let's just get to it. And I don't think I wrote this question, and I don't remember where I got it from, but let's just go through and read it. The Hubble Space Telescope, or the Hubble, yeah, I didn't write that. I know I didn't write that, has a mass of 11,100 kilograms and a circular orbit at an altitude of 560 kilometers. Calculate the speed, what's the period, and what is the work needed to put it in orbit. Okay, so A, what is the speed? V. So the magnitude of that, of course, is moving in a circle. Remember that we have we have the momentum principle. It says that F net is the rate of change of momentum, dp dt, where momentum is mass times velocity. Now, we've really done two kinds of problems. One where we can calculate all the forces and then we can use that to say something about how the momentum changes, or we can know something about how the momentum changes. And there's two special cases of change momentum. I have this dp dt equals 0, right? That we call equilibrium. If the change momentum is 0, then the net force has to be 0, and we call that equilibrium. And the other case we have is where the magnitude of dp dt, the magnitude of that vector, is equal to mv squared over r. This is for circular motion. If an object's moving in circular motion, the change in momentum is pointing towards the center of the circle, and the magnitude is mass times velocity squared over r. We call this centripetal force sometimes, but it's not that big of a deal. Centripetal force, because it has units of force. Center pointing force. So the Hubble is indeed moving in a circle, so we can use that. In this case, I know I can go ahead and write the change in momentum as mv squared over r. Now, be careful here, because r is actually this value. It's the radius of the circle, and we're given the height as h. So r equals the height, the altitude h, plus the radius of the Earth. Just so you know, that's what we're talking about. Now, what force is acting on the Hubble to make it move in a circle? Well, that's the gravitational force, Fg. So I only care about the magnitude because the directions are changing all the time, so we don't have to put that in. So I can just use the magnitude of the gravitational force. It's g times the mass of the Earth times the mass. This is the mass of the Hubble, right? It's the object that's moving in a circle. So that's the mass of the Hubble divided by r squared. Now, I just want to solve for v. So let's solve for v. So v is going to be, that cancels. So I get v is the square root of g, mass of the Earth, over r, and I'll go ahead and put radius of the Earth plus h in there. Let's go ahead and calculate this. I'm going to put in the numbers. So g, I'm not going to put the units. 6.67 times 10 to the negative 11th. Mass of the Earth is 5.97 times 10 to the 24th. And this is going to be equal to the radius of the Earth, 6.73, I think it's 73, times 10 to the 6th, plus 560 times 10 to the 3rd. And let's put all that in our I'm going to use a calculator to see if I can do this correctly. Okay, I have calculator issues. I don't know if you know that, but I don't always do the best job with the calculator. Okay, so I'm going to say square root. You know, when I was using a calculator, when I was in school, there was no command line. It was just numbers. You couldn't enter a series of expressions. You had to do one operation at a time. That's the way we did it. Okay, now if you enter these in scientific notation, you're going to be much better off because you don't have to worry about the order of operations between the numbers. So I'm going to say 6.67 scientific notation, negative 11th. Now that's just one number. I don't need to worry about parentheses, times 5.97 scientific notation 24 divided by, now I have a sum in the bottom, so I do need a parentheses down there. 6.73 scientific notation 6 plus 560 scientific notation 3, close parentheses, enter. Okay, so I get, what's that? 7391. 0.7391 meters per second. So that's pretty fast. Okay, that's actually kind of useful in the next thing. Well, it's actually positively useful in the next thing, the period. So let's say that, let's calculate the period. And this is the time it takes to make one complete rotation. And we call that t, period. So let's just say the velocity is the change in position with respect to time. Well, if I think about that, even though it's changing directions, I can think of this as one-dimensional direction. And how far did it go? If I go all the way around, how far did it go? Well, it went 2 pi r. And how long did it take? It took t. So if I solve that for t, I get t equals 2 pi r over v. And I already have an expression for v, so I can write this as 2 pi r times the square root 1 over v. It's going to be 1 over this. And I'm just going to write that as r. So that's going to be r over g times the mass of the Earth. And then I can bring that in if I want to. You don't have to. So I get 2 pi times the square root of, if I bring the r in, it's going to be r squared. So I get r cubed. And then I can write this as radius of the Earth plus h cubed over g times mass of the Earth. So let's calculate that period. So it's going to be 2 times pi times the square root of 6.73? Yeah, 6.73 plus times 10 to the 6th plus 560 times 10 to the 3rd cubed. All of that over 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th. Okay, let's do it. Yeah. The units, I mean, we can check the units. I'm pretty sure the units are fine. Okay, clear 2 times pi, where's pi? Pi times the square root. See, I pushed that one a lot because I can't see it. And then I have to add these two things together, so I'm going to put parentheses again. 6.73 scientific notation 6 plus 560 scientific notation 3, close parentheses, hat 3. Now, I don't think I need a parentheses around that whole thing, so I'm just going to say divided by parentheses 6.67 scientific notation negative 11 times 5.97 scientific notation 24, close parentheses equal. Is that, I think that's wrong. 6198. 6198. Yeah, seconds. If I divide that by 60, I get that time in minutes. I do know the answer, so say divide by 60. Okay, that's right. 103 minutes. That's right. I'm kind of surprised with myself that I got it right, because I'm not really good with the calculator, you know that. Okay, final question. What is the work needed to put the Space Telescope into orbit? So let's start right here. Earth. Position 1. That's my telescope at position 1. I'll draw it a bigger orbit than it actually is. And up here, position 2 with a velocity. Okay, so I'm going from 1 to 2. And of course, we're using work is the change in energy for two reasons. Number one, because we don't care about the time. I don't care about how long it takes to get up there. I care about a change in position. It's going from position 1 to position 2. And then number two reason to use work energy, because it says, what's the work? So you have to use work energy. So you could try to calculate the force needed to get it into orbit, but that's not a constant force or constant direction. That everything's complicated. So instead, let's say the system is the Hubble Space Telescope plus the Earth. In that case, this whole thing, I only want to look at what forces do work on that. and that's whatever this rocket is or whatever. I don't really care what it is. I'm just going to calculate that as the work. And then I just need to find the change in energy of the system. Let's assume the Earth doesn't move. In that case, I have a change in kinetic energy plus a change in gravitational potential energy. Because I have these two together, I can have both those. So remember, kinetic energy is 1/2 mv squared. Potential energy is negative g, mass of the Earth, mass, and it's mass of the Hubble, over r. So let's say this is going to be work, is the change in kinetic, K2 minus K1 plus U2 minus U1. Now, which of these values are 0? There's only one, right? Because if I assume I'm starting from a non-rotating Earth, and we'll talk about that in a second, then the initial kinetic energy is 0. It starts on the Earth. So this is 0. But neither of these are 0, because the only way for the potential to be 0 would be to be an infinite distance away, right? R goes to infinity, the potential goes to 0. So none of those are 0. So let's just calculate. Let's put in expressions for these. So work is the final kinetic energy, 1/2 mv2 squared, plus the final potential energy, negative g, mass of the Earth, mass, over r. But this r2 is going to be equal to, let's just say r2 is r radius of the Earth plus h, right? That's where it ends up. So radius of the Earth plus h, and then minus a negative, so plus g, mass of the Earth, mass, over the radius of the Earth. And I already know the value for v, but I mean, I can get it too. So let's actually write this as an expression. Remember, v is this v2, the square root g, mass of the Earth, over r, which is the radius of the Earth, plus h. And if I square that and put that in, I get work equals 1/2 times m times g. So right, this is g m over the radius of the Earth plus h, minus that term, g m over the radius of the Earth plus h, plus g, mass of the Earth, m, over the radius of the Earth. And you'll see that I have a little combination here, right? I have 1/2 and then 1. So this is going to, these two together are going to give me negative 1/2. And I'm going to factor out the g and the m and the e, and I get g, factor this out. Let's factor out g, m, all of that. And then I have these two terms together are going to be minus 1/2 radius of the Earth plus h. And then that term is going to be plus 1 over the radius of the Earth. I think I did that right. Okay, let's put all these numbers in. I'm not even going to write them down. I'm just going to do it because that's how I roll. Put this right here. Let's move this to the side. Right there. Right there. How about that? Clear. Okay, 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97 times 10 to the 24th times the mass of the Hubble. Now I do need that in here. So that's 1.1 times 10 to the third. It was 11,000. Times parentheses. I'm going to say, let's do the other way around. So 1 divided by the radius of the Earth, 6.37. 6.73. What is it? I may have used the wrong number. I've said 7.3. 7.3 times 10 to the 6th. I'm doing this. Minus 1 divided by parentheses 2 times parentheses radius of the Earth, 6.73 times 10 to the 6th plus 560 times 10 to the third, close parentheses, close parentheses. I think I need one more. Okay, I think that's right. So this says the energy is, the work done is 3.5 times 10 to the 11th joules. Okay, so that's the answer to that question. Now, this leads to the second question, which I will not answer right now. I will answer later. This assumes that the Hubble Space Telescope starts at rest on the Earth, and it does not, right? If the Earth is rotating, then it's moving due to the rotation of the Earth, and that speed depends on where it is on the Earth, right? If you're at the equator, it's going the fastest. If you're at the North Pole, it's not going that fast. So you do need to take into account the rotation of the Earth, and it does give you a little bit of a boost, right? But here's the thing that I'll let you calculate on your own. When you do the work to get this into orbit, you have to get it up high, and you have to get it going fast. At this case, 85% of the work goes to kinetic energy. So it's really about getting it fast. It's not so much about getting it high. But there you go. The end.